All right. Hey, everybody. Continuing topic 30 today with boosting ensemble methods. But before we get into that, still a few of you haven't submitted your blogs, so please get that done. So there's blogs. Also, there is, project. If you haven't yet, I think now is a good time before the end of the week to just take a look at some of your data sets. And please let me know which data set you're going to go with. Even if it's one of the provided ones, let me know which one you want to go with, just so I have an idea. And if a bunch of you are working on the same data sets, maybe y'all can collaborate. So please let me know which data set you are working on. Now is a good time to start exploring them, because today's models, tomorrow is going to be the last of the classification models we're going to talk through. Again, they all work the same way through scikit-learn anyways. Cool. Questions regarding project, anything so far? All right, let's get into boosting then. Okay, so first, we're going to set up boosting in a way where we contrast between what we did yesterday, between bagging methods. And remember, both bagged trees and random forests are methods of bagging, are bagging methods of bagging ensemble methods. And we are going to talk about two specific boosting methods, AdaBoost and gradient boosting, how they differ and how they each make predictions. All right, so boosting, which was originally, when it was first conceptualized, was called hypothesis boosting. And what it does is it refers to any ensemble method that can combine several weak learners and their mistakes into a strong learner. So what is a weak learner? Basically a model that doesn't perform very well. So whereas yesterday we were doing this process of aggregation, imagine we're training a bunch of different trees on slightly different sets of data, and then we're aggregating them after the fact. So you can, if you're thinking about when the trees are being produced, it doesn't really matter when each of your 100 decision trees are being trained in your random forest. For boosting, they are trained sequentially, and we'll kind of see how that is done, but you have to build it tree by tree, because each subsequent tree is going to take into account prior errors, and it slowly gets better and better. So yeah, the general idea of most boosting methods is to train predictors sequentially, each trying to correct its predecessor. So rather than just training a bunch of things in parallel, you have to wait for one tree to finish training, figure out what the errors are there, and then you slowly, improve on those errors. So there are many boosting methods available. So there's more than just these two. So the most popular are AdaBoost, which is short for adaptive boosting, and gradient boosting. You'll see that gradient boosting, there's another version of gradient boosting that we'll talk about at the very end of this slideshow called XGBoost. If anyone has ever perused Kaggle or towards data science when it comes to best classifiers, XGBoost actually has historically performed very, very well. So I wouldn't be surprised if for most of your projects you end up picking XGBoost as your best model, but we'll talk about that later. Okay, so again, to contrast bagging versus boosting, because this distinction is pretty important, and they do ask this at interviews sometimes, the difference between bagging and boosting methods. Both are ensemble methods because they combine multiple learners, but again, bagging is done in parallel, right? Each of these is a decision tree, and you aggregate their results however you want to aggregate them. And boosting, you can see that the arrows kind of connect each of them. They kind of string each one together. So it's sequential. You have to build one tree after another. Okay. So boosting is a statistical framework that whose objective is to minimize the loss of a model by adding weak learners using a gradient descent procedure. So very similar to how, in the first couple of models that we talked about, there's a cost function within decision trees. There's a cost function of, you want to get the partitions as pure as possible. We can use some sort of error metric to improve upon. So instead of adjusting parameters to get one best performing model, we can just stack models on top of each other to try and slowly reduce the error, picking parameters for your next tree to improve parameters from before. So this allows different loss functions to be used, explaining the technique beyond binary classification to support regression, multi-class classification, and more. So we won't really talk about the specific loss and cost functions just because it is pretty complicated, but we'll talk about conceptually what's happening. So boosting algorithms don't only exist for trees, but is also a general procedure that other classifiers can perform. So before we get into that, I do want to show you all an example. Let's see, where is that scikit-learn? There we go. So similar to how yesterday when we talked about bagging classifier, the default is to use a bunch of decision trees, but if you wanted to, you could bag other models. For AdaBoost, it's kind of similar. So you can see that the base estimator, if none, the base estimator is a decision tree classifier initialized with max depth of 1. So you can see that it's going to start with a very, very weak tree, and it's just going to keep building trees with max depth of 1 over and over again. And we'll talk about how that is done. But if you wanted to, you could instantiate an AdaBoost classifier with a different algorithm. Maybe you want to try like a k-nearest neighbors boosting classifier. You can do that too. So just in case you were curious. Okay, so yeah, other classifiers can also perform boosting. Questions about the whole general idea of boosting before we move on to specifics?
If you use other algorithms, they're going to use their defaults if you just pass in the regular algorithm, and then you can, I assume you can put in the actual like
hyperparameters that you want.
Yeah, inside as you're putting it into the AdaBooster.
Yep, absolutely. So if you put base estimator equal to k-nearest neighbors without any like specified hyperparameters, it's going to use this default of 5 neighbors. But if you want to have like k-nearest neighbors with like n equal to like n nest, what was it, k neighbors or n neighbors equal to like 10, and they will all be looking at the 10 nearest neighbors. So yeah, you can pretty much, you have a lot of flexibility to choose what your base estimator is, but you'll see why in a sec. But typically you want to have like a fairly inaccurate model. Like you want one that can like classify the obvious data points so that you don't have to worry about those in your later iteration. So usually you pick like a classifier that is not like awful, but one that is doing not the best yet, and then you slowly improve over there. Can also lead to overfitting, which we'll talk about in a little bit too. Okay, so let's talk about AdaBoost to start. So AdaBoost is adaptive boosting. And so let's just imagine in this scenario, our base estimator is a decision tree with max depth of 1. So max depth of 1, meaning that just means that for each decision tree, we're only looking for a single split. We're only looking for a single split for our data with each of these classifiers. So let's just say we have 3 classifiers over here, and then we're just going to make a single split for each. It's just going to be one tree that has like 2 options, true, false, whatever the condition is, we'll see. So let's just say this is our original data set, and we have these 5 minuses, these 5 pluses. With this very first tree, it's going to say, all right, this partition over here is the best split. Now, based on this best split, what AdaBoost will do is look at what data has been misclassified. So under this split, we have this minus, this plus, that was misclassified. So with these misclassified data points, for the next tree, you're gonna update the weights. And what update weights means is for anything that was misclassified, we're gonna weight that data point stronger. We're going to focus more on those misclassified data points. And we'll talk about specifically how they do that in a little bit. But now with these, you can see, well, I don't know if it's super clear, but these 2 minuses and this 1 plus over here is enlarged. And then because it's enlarged, when you feed the data through the classifier again, likely it will choose a different split because of the different weighting of the different data points. And so with the second one, all right, it says that this is going to be our split over here. Now, this is our split over here. What else is misclassified? These 3 minuses were misclassified. Then it says, okay, now with these 3 minuses misclassified, let's increase these 3 minuses weights even more. And it does this process, and then it picks a split over here where, and then it keeps going over and over again. And you have a bunch of different misclassified points at each one max depth of 1 decision tree. At the very end, you combine the results of each of your classifiers, aggregate them. We'll talk about how the aggregation is done. And then you have this combined classifier that does pretty well. So now this becomes the decision boundary. Let me just draw it so it's a little clearer. This line over here becomes the decision boundary, and you can see everything is now correctly classified. Questions about the intuition of AdaBoost? Okay, so AdaBoost just looks at misclassified data points and tells your model to focus more on misclassified data points at every iteration of weak estimator. All right, so the steps to adaptive boosting. First, you fit a base classifier like a decision tree. That was our very first step that we had over there. Then we're going to use that classifier to make predictions on the train set, which is what we tried to do over here. We try to make predictions. So misclassified 0.1, 2, 3. And then we're going to increase the relative weight of those instances that were misclassified and then train another classifier using the updated weights. And then we aggregate all of the classifiers into one, weighting them by their accuracy. So based on this, you can maybe say out of 10 points, this has an accuracy of 70%. This has an accuracy of 70%. This one is of 60%. And you're just going to aggregate all of the results together, use some voting, some weighted voting based on their accuracy, and you'll get this combined classifier. Cool. This is the math that goes behind boosting. Basically what's happening here, you're going to initialize some observation weights. So at the very first step, every point is weighted equally. So therefore weight equals to 1 over n. Let's just say you have 10 data points. Each data point is going to have a weight of 0.1. For m equal to 1 to m, and m being the number of estimators that you want, you're going to fit a classifier. And we're not going to go through all of these right now, but with each classifier, we're going to compute the error, which is how many data points was misclassified. How many data points misclassified over all of the data points. So accuracy, basically. This is not too important, but this helps you compute how you should eventually weigh each classifier when you're doing your aggregation. So it's actually aggregated using something that looks very similar to the oh my gosh, what am I trying to say? The logistic regression sigmoid curve to force the probability between 0 and 1. And then you re-weight everything. You weight it based on what was misclassified. So anything that was misclassified, you're going to weight that higher, and then you just repeat that process over and over again. And then your final classifier is going to be a summation of your weighted results. The math that goes behind this is actually not that important. You actually don't really get asked about specific boosting algorithms, just because in different models, there are different ways to compute this and this step over here. With different AdaBoost models, and actually different boosting models might work very similar to this, but just have different math formulas that go behind these steps. So it's not super important to remember the math of this. But if anyone is curious, this is how it's done. Okay. So what happens here, if you remember how we had the process of bootstrapping before, what happens is that the first classifier is trained using a random subset of the overall training set. And misclassified items are assigned higher weights so that they appear in the training subset of the next classifier with higher probability. So it's kind of like doing bootstrapping again, but instead of bootstrapping in parallel, we're bootstrapping based on probability, because remember with bootstrapping, we're sampling with replacement. Now the replacement samples, the sampling with replacement just means that there's a higher chance that you'll draw more instances of your previously misclassified data. So that's how it prevents, that's how it decorrelates subsequent trees. Cool. And in weighting the classifiers, again, we talked about this earlier. How do you aggregate? After each classifier is trained, a weight is assigned to a classifier based on its accuracy. More accurate classifiers are assigned higher weights to have more impact on the final outcome, right? So usually what you'd expect is the first few classifiers won't be weighted very highly, but then as you get more and more accurate, as you get a higher and higher accuracy, as hopefully you would, as you keep boosting your model, those will get weighted even higher. Again, the math formulas are not super important for this section. All right, So for regression and classification, AdaBoost has a regression counterpart as well. So that makes it very neat if you ever wanted to, redo a regression project or do a regression project for perhaps your capstone or something. You can employ boosting methods too. And they're very, very similar. You start with weak trees, and then here you use a misclassification penalty. And the only difference here is you use some sort of loss function, because in a regression, you don't really have misclassification. You use maybe like a root mean squared error or mean squared error, mean absolute error, basically an average error. And that's how you slowly reduce that's how you boost basically. All right, some things to note for AdaBoost. First, the quality of data. So because ensemble methods continue to attempt to correct misclassifications in your training data, you have to be very careful that the training data is of high quality. And what does high quality mean? You don't want to have too many outliers, and you don't want to have too much noise. So if you think about how boosting works and how the presence of outliers might affect it, if you have outliers that maybe you have just one data point that, like, based on its features, it should be classified one way, but it just so happens to be another way. Because of how boosting works, that weird outlier is going to keep getting resampled. It's going to keep getting resampled in subsequent estimators. So your model is really going to focus on the outliers. And so maybe you want that, maybe you don't. But yeah, outliers will basically force the ensemble down the rabbit hole of working hard to correct for these unrealistic cases. So these could be removed from the training data set. Next, also, if you have noisy data, specifically noise in your output variable. So let's say if you had a classification problem with like 20 classes, it actually can start to reduce the overall performance of boosting methods, because it's going to get to start to overlearn. Basically overfitting. Boosting models are just very, very prone to overfitting because it's trying to overcorrect for every single misclassified data point. Cool. So as summary, it sequentially trains classifiers. It improves classifiers by looking at misclassified instances or high error data points if you're thinking about regression. And then it ups the weights of misclassified instances, so they're more likely to be included in the next training data subset. And then you aggregate the classifiers together by weighting them based on each of their accuracies to create the final classifier. And things to note, if you have a lot of outliers, you'll start to notice that it doesn't perform as well because it starts to overfit. And also that AdaBoost can use any type of classification model, not just decision trees, as we saw from our scikit-learn documentation. You can just input any base estimator you'd like. Awesome. Before I move on to the next kind of boosting, any questions? Okay, so before I get to that, how should you prep your data for boosting? So by default, the base estimator, I would say it depends on your base estimator. That's the answer. It depends on your base estimator how you want to prep your data. If your base estimator is decision trees, if you want to just use the default decision trees, you don't have to worry about like scaling and all of that. However, if your base estimator is a k-nearest neighbors model that is distance based, so therefore you would want to standardize all your features, you have to do that if you're using like k-nearest neighbors or logistic regression in your what am I trying to say? As your base estimator. You would want to scale your data prior to fitting an AdaBoost with a k-nearest neighbors base estimator. So whether you scale data depends on what your base estimator is. Cool. All right, let's talk about gradient boosting now. So just like AdaBoost, gradient boosting evaluates the collection of trees sequentially and then gradually ensembles a collection of trees that model the underlying behavior of our data. So unlike AdaBoost, what gradient boost does is it evaluates the residuals of the previous tree and tries to make predictions on the residual. So instead of trying to, just take the same training data and, sample different data points based on their misclassifications prior, what it does is you're actually training the model on its residuals, which is really kind of interesting. So very, very similar sequence of math. However, here, what we're doing is we're initializing a model with a constant value. Yeah, wait, hold on. Yeah, we're initializing a model with a constant value, which is the loss function. And this is actually, these are the formulas for regression. Okay, never mind. We can talk about regression anyways. So initialize this loss function. And this loss function will basically be how you use what you use to determine the residual for every model. So let's just say you have your linear regression model. Remember how we had model.resid when we were doing linear regression? It's actually going to build a second regression just to try and predict what the errors are. So yeah, that's what's happening here. So you're fitting a regression tree here, compute this loss function, and then update to try and predict the original plus its residual. So we'll get into that process in more detail. I think this math is a little bit confusing.
Sorry, was that referring
yes.
to the decision for forest regression or the linear regression?
This is specifically a decision tree regressor, but the way that you compute loss for any regression can be like a mean squared error. So here they don't really tell you what it is. It just uses L as a general error, but you can sort of think of it in a very similar way. When you fit a decision tree regressor, you are going to have residuals as well. And you would just build a second decision tree regressor to try and predict those residuals.
Right. I guess my question is, if you use linear regression instead of decision tree, will it just make a new linear regression each time instead of?
Yes, absolutely. That's right. Yeah, you can do a gradient boosting regressor and you can feed it in a linear regression if you want as well. So we take a look at gradient boosting regressor. Let's see, here we go. You can give it a, where is the base estimator? Well, I guess by default, does it use trees? I'm pretty sure in some of them, you can give it a base estimator. Never mind, maybe not this one. No, I'm pretty sure there is a way to instantiate it with a different estimator.
I guess so, estimator, you skipped over.
Oh, yeah. Let's see. Okay, never mind. Oh, isn't init? Oh, here it is, the init. So yeah, you can use, no, it's not this one either. Never mind. I have it somewhere in the, yeah, just ignoring this, theoretically, you could feed it in a linear regression and then just build multiple linear regressions to predict their errors. And that is the process of gradient boosting. But yeah, I wonder where we'll worry about that later.
Thank you.
You're welcome. Okay, so let's just say we have this data set and we are trying to predict y using x. And this is a regression example because for gradient boosting is a little easier to think about it in a regression under a regression framework. So obviously not linearly related, but maybe a decision tree regressor can help to make some predictions on this. So this is what iterations would look like under gradient boosting. So let's just say that here, each of these red lines are the predictions, and each of these green points are their respective residuals. So let's just say at iteration 1, this is our prediction. We have a bunch of residuals, and I think the residuals are not labeled properly. So let me just draw some lines real quick. So based on this, the residual line would be roughly here, as in this would be 0 for residuals because it fits this perfectly, and it has residuals like that. As you move on, it's going to try and build building a new model to try and fit this. So this red line over here is taking this into account, these residuals over here. And then over time, your residuals are going to start getting lower and lower. I think the scales of the axes of these graphs are not consistent, but basically you'll see that these residuals will slowly converge to 0. So this is iteration 1, 2, 3. By iteration 18, 19, 20, you can see that the residuals start to go around 0 because each model is taking into account residuals of the prior one. And so it starts to understand error over error over error. And so that's how it slowly gets to fit. Questions about this? Point being, overall residuals will start to converge to 0. which can lead to another problem. So we'll talk about that in a couple slides. All right, so validation error and number of trees. Let me get rid of that green line. There we go. Validation error and number of trees. Validation error was basically like test set error. And this is a very, very typical graph that you see when you do your like train test split and get your testing error. So it starts really, really high and it reaches some sort of minimum. But because the way that boosting models work, it works very hard to correct for residuals in kind of a similar way as AdaBoost, but instead of like reweighting the data point, it's literally fitting a model on residuals. It has, it's very, very prone to overfitting. And so if you were to plot number of trees or number of estimators versus the error, you can see that after a certain point, the error is going to start going up. It's not always this plateaued. I've come across gradient boosting graphs that can even look something like this. It goes to a minimum and then shoots up because it really starts to overfit specific like outliers, for example. And your best model, you can see it kind of fits the line, not hitting every single data point, but fits pretty well. If we take a look at the next slide, let me clear all of these drawings. Oops. All right, we take a look at this next slide. This is bad quality, but this is roughly what the prediction lines will look like. This is 3 estimators. You can see that there's like a little bit of jaggedness here, but it's obviously not predicting any of these. But with 200 estimators, it starts to overfit to each data point. So you can see like here, there's a lot more, I don't know what's the word for it. There's a lot more variation. The line is a lot less smooth versus this is 200 estimators versus 55. So you start to get patterns like that as you go deeper into your boosting. Cool. Similar as AdaBoost, we can talk about gradient boosting in the framework of regression and classification. So we talked about regression, and with regression, we talked about minimizing the cost function, and the cost function being very likely would be like root mean squared error, one of those. And we're creating new trees using the gradients from the prior trees. For classification, very, very similar. The only difference is our loss function or our cost function is it is maximizing log likelihood. So it's a very similar process of how we went from linear regression to logistic regression. You know how in linear regression, our cost function was our RMSE, but for or sum of squares, residual sum of squares. And for logistic regression, we're trying to reduce the error via maximum likelihood estimation. And so maximum likelihood estimation is the cost function or loss function that's being used for classification trees and gradient boosting. So it calculates the partial derivative of log probability for all objects in the data set. And log probability is basically, I wonder if you can find it here. Is it at this one? It's not at this one, but I know, let me think, what's an example? Let's go with naive Bayes. Scikit-learn, naive Bayes. Okay, so any model, you can get the log probability of prediction, which is here, yeah. Predict log proba, it uses that to perform gradient boosting on. Okay, and then same process, you're just going to create new trees over new trees based on those errors. Cool. So I did mention this at the very start. Gradient boosting has, okay, rephrase. There's another kind of gradient boosting known as XGBoost. And XGBoost stands for extreme gradient boosting. XGBoost is actually not from the scikit-learn library, but it works in the exact same way. You just have to import something different. It has the same .fit, .predict methods. I think the only difference for XGBoost, if you wanted to get like the feature importances, like we talked about yesterday, feature importances is slightly different, but you can still get them through XGBoost. So XGBoost follows the principle of gradient boosting. However, there's a slight different process for XGBoost. Basically, XGBoost really takes into account the overfitting. So if you were to compare gradient boosting and XGBoost automatically takes into account regularization. You don't even have to tune the regularization parameter, although you can, but it automatically corrects itself for overfitting. So there's a much lower tendency to overfit an XGBoost model compared to gradient boosting, even though the underlying concept of how XGBoost models trains very, very similar to gradient boosting, because it is a derivative of gradient boosting models. So yeah, basically uses a more regularized model formalization to control overfitting, which gives it overall better performance. The name XGBoost refers to the engineering goal to push the limit of computation resources for boosted tree algorithms, which is the reason many people use XGBoost. So what this is getting at is, you know how let me see if it's here. You have, yesterday we talked about, which one was it? Random forest. So we talked about random forest and we talked about that njobs parameter, which is over here. njobs parameter basically says how many of your cores can you use. For bagged classifiers, because you're pretty much training different versions of the data set in parallel, you can technically, I mean, I also personally don't know how exactly this works, but let's say you have like 8 cores on your computer, you can be training like 8 models at the exact same time. For boosting, you can't really do that because you rely on the output of your previous model to build your next one. So you have no choice but to just wait for your models to train sequentially. So because of that, boosting models actually take a long time to train. Again, also, it's all relative depending on the size of your data set, but it can take a very, very long time to train. What this is getting to, where like how XGBoost tries to push the limit of computations, is XGBoost tries to make it a little bit more efficient. It's to the extent that I'm not sure how they do it either, but XGBoost runs faster than gradient boosting because they're trying to parallelize as much computation as possible, which means that it's like whenever it can split the work amongst multiple cores of your computer, it will try to do that. So XGBoost will also just run faster than gradient boosting. Cool. So yeah, it's just known to be harder, better, faster, stronger. It's like a classic like Kaggle competition winner algorithm. You can also give it your own unique cost function if you want. I will say, like, even I've never done that, but you do have the functionality to do that if you wanted to. And also mathematically, the cost function has to be twice differentiable because it uses a Hessian in the gradient descent algorithm. That is a sentence that is not relevant to data science at all, but if you have like calculus knowledge, then you will know what kind of cost functions you can input for your XGBoost model. And also, yeah, it has built-in regularization, L2 by default, that is based on the node weights. So yeah. Cool. And finally, a bunch of resources over here. That is boosting, and that ends our ensemble models. I don't think, yeah, I have no more slides here. Cool. Any questions at this point? All right, so we only have one more model to talk about tomorrow, which is support vector machines. At this point, again, very, very good idea to start deciding on your data set for your project. We'll talk about it at our one-on-ones coming up this week, or just Slack me what your data set is, just so I have an idea of what you're working on. And when we're talking about questions, I know what examples to use. So please let me know what data set you're using. In terms of level of understanding, I do want to reiterate, I would say at the end of this phase, I don't expect you all to be experts at every single model we've talked about so far. These are things that they come with experience, they come with, just time. You don't have time right now to sit down with each algorithm. I'll tell you, for like in like college courses for machine learning, it's an entire week per algorithm, and we spent like not even like a full day on each. Like I think some days like today we have to talk about like 2 different ones. So yeah, you're definitely not expected to fully understand every single algorithm. Although whatever your final model you choose for your project is, I do request that you at least you just do more work for that algorithm. Try and understand the algorithm a little bit more if you can, because very likely this project is one that will definitely go on your resume, and you're going to mention what model you you ended up picking, and interviewers are definitely going to ask you about the model. So if you just spend the time now to just learn the one, maybe if you have a runner-up, do that too. But yeah, that's my request for like how much understanding to have at the end of the phase. Cool. Any questions on that at this point? Awesome. Well, if there's nothing else, tomorrow we have our last study group of the phase, which is insane. I feel like this phase has flown by so quickly. But yeah, we'll talk tomorrow. I'll set up an office hour schedule I'll tell you all what I'll be talking about over the office hours. You'll see it on your homeroom for next week because your presentation will be in a week. Again, for these presentations, it doesn't have to be like your final presentation, because I know, you still technically have up to 2 weeks after Friday to keep working on it. But for your Friday presentations, wherever you're at. For those of you who have written a function, you can pretty much already get your modeling results right after you're done cleaning your data. So happy to talk about that during next week's office hours. Cool. Well, if there's nothing else, I will see you all tomorrow back here at this time. Any questions you have, as usual, you can Slack me if you need. All right. Bye, everybody.